Friends, welcome to the concept image segmentation. Segmentation is to subdivide an image into its component regions or objects. Segmentation attempts to partition the pixels of an image into groups that strongly correlate with the objects in an image. So what is here the segmentation? It is simply grouping the objects. Okay, how to group the objects of an image? We can group the objects by if the objects are with the same color, or the objects are with the same intensity, or the objects are separated by some boundaries. So that is the division of objects or dividing the image into different objects or regions is called segmentation. Segmentation is typically the first step in any automated computer vision application. It is the first step to do any analysis of the image. Segmentation should stop when the objects of interest in an application have been isolated. I'll show you the example. See the example, coin image and the tiger image. See here, all these coins are divided into different groups. See, depending on the size of the coin, yes, it is segmented like this. For different sizes of the coins, yes, here different color is allotted for that circle. So this is called segmentation. So allot the same color for all the circles. No problem. The smaller circle indicates the small coin and the bigger circle indicates the bigger coin. Suppose if you see this image, yes, here is the sand. This is all the grass and this is the tiger. So and this is the water. So if you see the segmented image, okay, each region or each object is separated like this, segmented like this. So if you observe the segmented image, we can identify this is the line and this is the grass, this is the water and this is the sand. And even if you see this example, here is the corn image having some fungus and these are all the regions. So now this gets segmented like this. Okay, and see this. All these small parts get segmented like this. After segmentation, you can analyze these regions in a clearer way and in an effective way. Then, segmentation algorithms generally are based on one of the two basic properties of intensity values. Then, how to segment the images? We have two things. We can segment the image based on the discontinuity, or you can segment the image based on the similarity. If you go for the discontinuity, to partition an image based on abrupt changes in intensity. Then, segmentation using similarity to partition an image into regions that are similar according to a set of predefined criteria. Means, if the objects are having same color, then you can segment. If the objects are same texture, similar texture, you can segment. If the objects are having same intensity, you can segment. Okay, so the first one is based on the intensity changes between the two regions, you can identify different regions and you can segment. And based on the similarity also you can segment. Suppose if you go for the examples, see this tiger example. The tiger is having similar texture, so that is the reason it gets segmented like this. If this grass is having similar texture, so that is the reason it is segmented like this. The sand is having similar texture, so this is the segmented region and this is the water. So this is the similarity, segmenting based on the similarity. Okay. And if you see this one, it is segmenting based on the discontinuity. If you see the background of image is a dark background, black background. On the black background, you are seeing many coins, means there exists transition of intensity between the coin and the background, between every coin and the background. So depending on that intensity change, you can segment the image. Now it is the detection of discontinuities. This is, see here the segmentation is based on the two things. The first thing is based on the discontinuity. Means if there exists different intensity changes. How are these intensity changes? These intensity changes are at the point intensity change, means if the intensity is changed by 1 pixel, then that is called point intensity change or point discontinuity. Suppose if the intensity change is in the form of a line, Means a line of pixels, the intensity is changed along the line of pixels, that is one discontinuity. If the intensity is changed in the form of edge, then that is another discontinuity. So totally under the detection of discontinuities, there are three basic types of gray level discontinuities: points, lines and edges. Is how to find these discontinuities. After finding these discontinuities only, we can segment the image. To find all these discontinuities, simply apply a mask. You already know how to apply the mask. Yes, it was explained in spatial filtering concept. Then I'll move to the point detection. What is a point? A point in an image is a single pixel that differs sharply in intensity, brightness or color from its neighborhood. Okay, then simply to understand, I'll tell you. Suppose take a white paper and with the pen you keep just one dot. The background is completely white, but there exists only one point which is black. So there exists intensity discontinuity. So that is called point discontinuity. Okay. Point detection can be achieved simply by using this mask. Okay. How to get that point? How to identify that point? A point has been detected at the location on which the mask is centered if mod r greater than or equal to t. What do you have to do? You have to apply this mask on the image. I'll explain with an example, no problem. Yes, you know how to apply this mask on the image. Every pixel of the image must be coincide with the center of this mask, and then you have to multiply the pixel intensity and the mask weight, and then you have to sum all those products. That gives the R. Anyway, I'll explain with an example, no problem. So if that response after the application of this mask is greater than or equal to T, what is T here? That is a non-negative threshold, and R is the sum of products of the coefficients with gray levels contained in the region encompassed by the mask. Yes, if it is greater than or equal to T, then you can say a point is detected. See the examples. First is X-ray image of the turbine blade. The second one, result of point detection. See here is the point. Here is the point. The circular one is the point. Yes, here is the point is detected. Here the point is detected. And result of thresholding. Yes, if you apply the thresholding concept, you know already the thresholding. In the thresholding concept, yes, you have to keep one intensity level as threshold. If the image consists of, if the pixels of the image consists of less than this intensity, then you have to make all those pixels as black, above this intensity as white. Okay, the result of thresholding is a binary image. So now if you take this pixel intensity as the threshold, below that value it becomes black. So that is the reason all this becomes black, and equal to and above this value it becomes white. Okay. Now coming to the line detection. What is a line? In an image, a line is a thin row or column of connected pixels that looks brighter or darker than the background. If you see, this is a region. Okay, suppose if I draw this line. Yes, see this. This is a line which is having connected pixels. Maybe brighter or darker. If as the background is bright, line seems to be dark. If the background is black, yes, you can draw a line which is bright. Yes, these are masks used to identify the lines. Yes, see the first mask. If you apply this mask, you see the weights. The top row of the mask consists of -1 and the bottom row consists of -1 and the middle row or all are 2. Okay, so if you see this, these are all -1s and these are all -1s. The center one is different. Okay, yes, now the mask below will extract lines that are 1 pixel thick and running in a particular direction. It is a line. Yes, what is this? This is 1 pixel. Okay, so that is the reason it is called 1 pixel thick line. The first mask gives the strongest response to horizontal 1 pixel lines with the maximum output when the line passes through the middle row. Okay, like the point detection, even this also I will explain. Like the point detection, if you apply this mask on an image, now you can identify a line when that line is passed through the middle row. Okay. So, yes, this middle row is in a horizontal. This mask is used to identify the horizontal lines. Same way, see this mask. If you apply this mask on the image, then you can identify a line in a plus 45 degree direction. Suppose if your image consists of a line which is in plus 45 degree direction, then yes, by applying this mask you can identify that line. Then third mask, you can identify a vertical line. With this mask you can identify a line at an angle of minus 45 degree. Okay, then if you see the values, sum of all these mask values, any of these masks, the total is 0. Because these minus 1s and these minus 1s, minus 6, and the middle are 6. Minus 6 and plus 6, 0. Means indicating a 0 response from the mask in areas of constant gray level. Suppose if the image consists of constant gray level, there is no discontinuity like lines, line discontinuity. Then what will happen? If you apply this mask on your image, then automatically the response becomes 0. Means there is no discontinuity. You are getting some value means there exists some discontinuity. Okay. So this is about line detection. Suppose, yes, here are 4 masks to identify horizontal lines, diagonal lines I can say, plus 45 and minus 45, and vertical lines. Okay. But in general, your image may consist of line discontinuities in any direction. Your image may consist of horizontal lines, vertical lines, diagonal lines means plus 45 degree, minus 45 degree, like that. Then how to identify? What you have to do? You have to apply every mask on the image. Let R1, R2, R3, R4 denote the responses of the horizontal, plus 45 degree, vertical and minus 45 degree mask respectively. If it is certain point on the image, Ri greater than Rj for all j not equal to I, that point is said to be more likely associated with a line in the direction of mask I. Suppose, what is the meaning of this? Suppose R1. Okay, means it is the response when you apply the horizontal mask on the image. If it is greater than R2, what is R2? Plus 45 degree mask. If the response for horizontal mask is greater than the plus 45 degree mask, then what it indicates? It indicates, yes, the line is in horizontal direction. The pixels which are in that direction, that horizontal direction, was more likely associated with the line in the direction of the mask I. Okay, suppose if R2 is greater than R3, means the line is in the direction of plus 45 degree. If R3 is greater than R4, the line is in the direction of vertical than minus 45 degree. In that way you can identify all the lines. Then, see the example. Binary image of a wire. This is the wire. After processing with minus 45 degree line detector, the minus 45 degree line detector is like this. This is the result after thresholding. I explained already the thresholding. If you see this image, just as an example, I kept this image, binary image consisting of all types of edges. Okay, starting from this first pixel, you have to apply every mask. Okay, then note on the value. Note on the value of response for every mask. Okay, if the response is greater than for one particular mask, than others, then that particular pixel belongs to that particular line. Okay, in that way, yes, you process all the pixels of this image. Yes, at last you can identify all these lines. Okay. Then coming to edge detection. Edge detection is an approach used frequently for segmenting images based on abrupt changes in intensities. Yes, an edge is a set of connected pixels that lie on the boundary between two regions. You have to remember. Yes, I think now you know the difference between line and edge. What is the line? A line is simply, see this example, see the line. A line is a line on a constant background. If a constant background consists of different intensity pixels in the form of a line, then that is called line discontinuity. Okay, means suppose if a line separates, suppose take this image, if this line separates the image, these are not different regions actually, these are having same intensities. Line. But what about edge? Edge is a set of connected pixels that lie on the boundary between two different regions. See here, this is one region and this is another region. Okay, it exists between two different regions. These are all different types of edges. This is a model of an ideal digital edge. This is a ramp edge. This is roof edge. Okay, see the digital edge? Ideal digital edge. Yes, this is all black and this is all gray level intensity, or I can say we'll take highest intensity. Fine. So the change or the transition from this intensity and this intensity to this intensity is very short. It's like stop. I can say it's a stop edge. Now if we see this transition from the dark to the light is gradual. It's like ramp. Okay. Now we see the roof edge. See the roof edge is, see suppose if you on the constant background, if you keep some pipe, like pipe, water pipe, if you observe on it top, it seems to be is in the center of the pipe like this, it seems to be brighter. And if you are moving away from this brighter side, yes, the intensity is decreasing. That type of edge is called roof edge. Okay. So this is stop edge or ideal edge. A stop edge is the simplest and most ideal type of edge. A stop edge occurs when the image intensity jumps suddenly from one value to another, similar to a stop in staircase. Okay, this is the ideal edge. So even the real images rarely have perfect stop edges due to blur, lighting or noise. This model helps understand and measure how real edges deviate from the ideal. Okay. Yes, means you can analyze any edge by taking the ideal edge as reference. So that is a stop edge, and these are all the applications of stop edge. So this is ramp edge. Yes, in practice, digital images have edges that are blurred and noisy, with the degree of blurring determined principally by limitations and the focusing mechanism. Example, lenses in the case of optical images, and the noise level determined principally by the electronic components of the imaging system. Anyway, you can read all these things. A ramp edge, see the definition, a ramp edge is a blurred version of the stop edge where intensity changes gradually over several pixels instead of one. See this. Here in the stop edge, the intensity is changing abruptly. In the ramp edge, it is changing gradually. Simply that is the ramp edge. Okay. Steeper slope means sharper edge. Gentler slope means more blurred edge. You are observing the blurring here. Okay. Less blur means the profile goes to like this. This profile becomes like this. More blur, then yes, this is the slope. There is no single edge point. Every point along the ramp can be part of the image. So this is single edge. This is the sharp edge. And here this is all edge, means the thickness of the edge is more. This is all considered as edge, so the thickness is more. Then coming to the roof. A roof edge is a type of edge that looks like the top of a roof. It rises in intensity to a peak and then falls again. I explained that already. See this, the center one is high intensity, and yes, if you are moving like this, the intensity is dropping. That type of edge is the roof edge. It is like inverted, the intensity profile looks like an inverted V or a narrow hill. Intensity increases to a maximum and then decreases. Okay. The width of the roof depends on how thick or blurred the line is. And yes, these are the different edges. Then how to identify the edges? So if you identify this edge, you can separate these regions. You can segment these regions. If you identify this edge, you can segment these regions. If you identify this edge, you can segment these regions. How to identify these edges? Edges can be identified using first and second order derivatives. You studied in image sharpening concepts, okay? You can just verify. See this. Yes, this is the image, let it be an image. This circle, for this circle, yes, this is an extended version of the intensity profile. Yes, for this line, just line. Yes, this part is in the darker side, so it is 0. And this is the edge part. The edge is not sharp, it is ramp, so that is the reason it is ramp. And after the edge, yes, it is bright, so this is the highest value. So this is the horizontal profile. So now the edge is a ramp edge. In general, 90% of the images consist of ramp edges. Okay, so this is the ramp edge. So how is the first derivative? See the first derivative. The first derivative is positive at the onset of the ramp. Means for this ramp, this is the plot of first derivative and this is the plot of second derivative. Okay. You can get the information about this first derivative and second derivative in the image sharpening concept. Yes, the first derivative is positive at the onset of the ramp and at points on the ramp, and it is 0 in areas of constant intensity. Okay, see this is constant intensity and this is constant intensity. That is the reason it is 0. Yes, it is positive at the onset of ramp. Whenever the ramp starts, it is positive, it is going positive. And along the ramp also it is positive. In the constant regions, it is 0. That is about first derivative. So, when the first derivative of an image, means in a simple space, in a simple region of the image, the first derivative is like this. So what you can say? You can say there exists some edge. Okay. Yes, the second derivative is positive at the beginning of the ramp. Positive at the beginning of the ramp. See, this is the beginning of the ramp. This is the beginning of the ramp, so it is positive. Negative at the end of the ramp. So this is the end of the ramp, so this is negative. 0 at points on the ramp. Yes, on the ramp it is 0. And 0 at points of constant intensity. See, here also it is constant. So, yes, for this space, for this considered space of the image, if the second order derivative is like this, then you can say there exists, yes, ramp edge. So, in that way you can identify the edges using first order and second order derivatives. This is all about the first and second order derivatives. I explained it. Now, behavior of the first and second order derivatives in the region of a noisy edge. See, these are all the first column or 8-bit images with values in the range 0 to 255 means grayscale images, and intensity profiles of a ramp edge corrupted by Gaussian noise of 0 mean and standard deviations of 0, 0.1, 1 and 10 intensity levels respectively. The second column first derivative images and intensity profiles, and third column second derivative images and intensity profiles. When there is no noise, okay, 0 mean and 0 standard deviation of Gaussian noise means there is no Gaussian noise. See the first derivative and second derivative. Yes, the first derivative and the second derivative are very clear. In a noise-free image, the first derivative is 0 in flat regions and constant on the ramp. The derivative image shows black bands, 0 and gray areas, constant slope. See here. Yes, you know, when the image is having constant intensity, the first derivative becomes 0. Yes, 0. So if you represent this as an image, then for this 0, these are zeros. Yes, during the ramp, it is positive. Yes, positive means highest value, so this is highest. And this is second derivative. Second derivative is positive at the onset of ramp, negative at the closing of the ramp. Okay. Then the second derivative, as this is a peak positive line, so this is positive line. As this is negative, it is the negative line, black line. This constant, gray areas represents no change. These gray areas represents no change. So these are the images of the original and the first order derivative and the second order derivative. What will happen if the noise increases? See, for this 0.1 standard deviation Gaussian noise, see this? See the noise? The second order derivative is more sensitive to noise. You are not able to identify the edges. See here, it's corrupted with noise compared to the first order derivative. And if the noise increases, totally the second order derivative is not giving any information. And for the higher noise, this first order derivative is also giving no information. Okay. So as noise increases, the derivative values fluctuate more. The clean constant gray band becomes uneven and or distorted. See this? See these distorted profiles. See the distorted profiles. Eventually, the derivative no longer clearly represents the ramp edge. Even small invisible noise in the image can make the derivative very noisy. This is about first order derivative. With even slight noise, the second order derivative becomes highly distorted. It's hard to find the positive and negative peaks as I explained. Therefore, the second order derivative is even more sensitive to noise than first. Okay. Then how to overcome this? Suppose if your image consists of noise and you want to find the edges. What you have to do? If you apply the edge detection using the first and second order derivatives, what will happen? Yes, you won't get any edges. You won't get any edges related information, so that you can't identify any edges, because the first order derivatives are very much sensitive to the noise. You are not getting any information where the edge locates. So that is the reason first you have to apply some filtering concept. Yes, because the derivatives amplify noise, image smoothing means the filtering must be done before applying derivative based edge detectors. First you have to smooth the image and then apply the edge detection using the first and second order derivatives. Okay. So this is the behavior of the first and second order derivatives in the region of noisy edge. These first order and second order derivatives are used to identify the edges. Fine. So now I'll explain in clear about the first order and second order derivatives. The first derivatives are implemented using the magnitude of the gradient. This, if for an image f of x comma y, the gradient is represented by del f, which is gx gy, a column matrix, dou f by dou x and dou f by dou y. This is called the gradient of the image, where dou f by dou x is a change in intensity along the x direction, and dou f by dou y is the change in intensity along the y direction. Okay. Yes, you have two directions, x and y, you know it. And the magnitude of the gradient is called delta f, which is, see the difference between f's. Okay. Yes, magnitude of this gradient is gx square plus gy square whole power 1 by 2, means root gx square plus gy square, or approximately you can take it as mod gx plus mod gy. This scalar value, this magnitude value shows how strong the intensity change. Suppose you apply this gradient on the group of some pixels on the region of some 3 by 3 or 5 by, you know, the neighborhood concept. So if you apply this gradient, if the gradient magnitude value is high, you can say there exists some edge. Okay. High gradient magnitude, sharp change indicates there is edge. Low gradient magnitude, smooth area indicates there is no edge. Okay, even with the gradient, you can find the direction of the edge also by taking the angle between these two components gx and gy. The angle represents the direction of edge. Obtaining the gradient of an image requires computing the partial derivatives dou f by dou x and dou f by dou y at every pixel location in the image. Okay, suppose if you go for only finding these derivatives in one dimensional, means along the x or along the y. So it is gx, dou f by dou x is f of x plus 1 comma y minus f of x comma y. Means there is, this is the difference between in the x direction. Okay, this is x plus 1 and this is x. And this is gy, dou f by dou y, it is f of x comma y plus 1 minus f of x comma y. Means it is the difference between y, two y's, y plus 1 and y. Okay, these two equations can be implemented for all values of x and y by filtering f of x comma y with the 1D kernels. Suppose if you plot the kernel for this equation, then it will be like this. This is minus f of x comma y is the first pixel, so that is the reason it is minus, and this is x plus 1 pixel, this is x pixel and this is x plus 1. You know x is increasing like this, so it is f of x plus 1 and comma y, and this is minus f of x comma y. And if you generate a kernel for this gy, okay, this is f of x comma y and this is f of x comma y plus 1. Okay, so that this is about 1D kernel. Okay, means you can apply either in x direction or in y direction. So if you want to go for diagonal, then there exists some special operators called Robert cross gradient operators, which are 2D kernels. Consider this 3 by 3 neighborhood of our image. Robert operators are based on implementing the diagonal differences. What is this dou f by dou x? Z9 minus Z5. See this Z9 and this is Z5. So you can find the edge along this diagonal direction. Okay. Why it is dou f by dou x? Z9. It is x plus 1 and Z5 it is in x. This is x now. This is the change in x now. This is x plus 1 and this this column is at x and this is at x minus 1. Means in the same way gy, which is dou f by dou y, is Z8 minus Z6. Okay, Z8 minus Z6. Okay, along this if it is y and this becomes your y plus 1. Okay, because y is increasing like this. You can generate a kernels for these two equations like this. Okay, the first one is Z9 minus Z5, so that is the reason it is, see this part is totally your kernel, 2D kernel. Yes, Z5 is minus 1, it is minus 1 and Z9 is plus, so it is plus. The remaining are zeros because you want to find only in this diagonal direction. And for this it is Z8 minus Z6, so it is minus 1 and this is 1. This is gradient operator for diagonal edges using Robert cross gradient operators. Okay. And so these are the various kernels used to compute the gradient. As explained, these are the Robert's kernels for this 3 by 3 region. These are 2D kernels. Okay, and if you want to go for more efficient edge detection with respect to some center point, what about the edge? Is it nearer to the center or farther to the center? So the effective way of edge detection is by using 3 by 3 gradient operators like Prewitt and Sobel. See the Prewitt? Yes, this top row is minus 1 and this bottom row is 1, the center is 0. So if you apply this kernel on the image, then what will happen? This is your Z7 minus Z1, then Z8 minus Z2, Z9 minus Z3. So you can get the horizontal edge, and by this you can get the vertical edge. And this is Sobel operators, Sobel kernels. This kernel is used to identify the horizontal edges and this is the vertical edges. These are Prewitt and Sobel mask to identify diagonal edges. See this, the diagonal. See the diagonal. Prewitt for diagonal edges and Sobel for diagonal edges. Whatever may be the kernels, if you sum all the values of the kernel weights, you will get 0.
What is the meaning? If you apply these kernels on an image, constant image consists of constant gray level, the value is 0. Means the image is not consisting of any edge. It happens even for line and point also. The kernel output gives 0. The response R is 0 means the image is a constant image. Okay.
This is the example. The first image is the intensity value scaled to the range 0 to 1. GX component means the horizontal edges. This is the C is vertical edges. And this the gradient image Gx plus Gy. So in this you are able to see only the horizontal, and this you are able to see only the vertical, and in this you are seeing both horizontal and vertical edges. And this is the same concept but with prior to the edge detection, prior to the application of the first order derivative, they applied smoothing with a 5 by 5 averaging filter. You know, the smoothing gives better edge detection. And these are the diagonal edge detection, diagonal edges for the same image, diagonal edges by using the Sobel masks. By using these two Sobel masks. Second order derivative is called Laplacian operator. It's a linear operator, and this is the expression. Second order derivative, dou square f of x comma y by dou x square plus dou square f of x comma y by dou y square. This is the expanded equation. You can verify in the image sharpening concepts. If you generate a kernel by using this expression, see the Laplacian mask. This is the basic kernel. Okay. And if you want to increase this 4 to 8, then you have to add some more minus 1s here, because the total value must be 0. Fine, that is the difference between these two. Okay, so yes, here is 4, here is 8, means plus 4 is added, means you have to go for another minus 4 addition. So this is minus 1, minus 1, minus 1, minus 1. This is the Laplacian mask used to implement the second order derivative. Laplacian of Gaussian, a very interesting and important concept, LOG, Laplacian of Gaussian. Laplacian effectively detect edges, zero crossings. Yes, this is zero crossing. See this zero crossing. This is zero crossing. Zero crossing indicates there is rampage. What is zero crossing? See this at the starting of the ramp you have positive. The second order derivative is positive, and at the end of the ramp the second order derivative is negative. If you connect the top and bottom of these positive and negative impulses of second order derivative, then this connection, this is the zero line. This is called zero crossing. Zero crossing indicates that exists rampage. The main drawback of Laplacian operator is it is extremely sensitive to noise in the image. I explained it. Second order derivative is more sensitive to the noise than the first order derivative. So even small intensity variations caused by noise produce large responses because the second order derivative amplifies high frequency components. So the Laplacian of Gaussian, so to overcome this drawback of more sensitive to noise and not getting proper edges, so we are going for the concept Laplacian of Gaussian, LOG. It first moves the image using the Gaussian filter, then applies the Laplacian. Okay. Yes, the Gaussian. So the advantage is the Gaussian smoothing removes small irrelevant fluctuations or noise before the differentiation. So the Laplacian acts on a cleaner version of the image. So obviously you are going to get good, means the effective edges. Laplacian of Gaussian combines Gaussian smoothing with Laplacian operator. So log of xy is del square of g of xy. What is this del? Laplacian operator. G of xy is a Gaussian function. See this Gaussian function. You are very familiar with the Gaussian function, e of minus of x square plus e power minus of x square plus y square by 2 sigma square, where sigma is standard deviation. So the Laplacian of Gaussian is this. So this is the Laplacian of Gaussian. You draw a mask, or if you generate a mask for that equation, then this will be the kernel, 5 by 5 kernel of that approximation. This is the plot of negative of LOG. This is del square g. The negative of LOG is this.
If you go for the positive, then this peak will become a dip. Okay. Then base negative of the LOG displayed as an image. Yes, the center one is highest. So the center is highest means the bright, and all other, the brightness is decreasing gradually. Yes, the brightness is decreasing gradually. And at this portion, you're having some dip. Okay, so it is going to be black, and then it is rising like this. So that is the reason it is some gray. Okay, then cross section of A showing zero crossings. You all know there exists zero crossings for Laplacian. And this is the mask used to find the LOG. So if you apply this mask on the image automatically, even if your image consists of noise, you're going to get sharp and clean edges. Okay. So this is all about detection of discontinuities in image segmentation. Okay. So we have totally 3 discontinuities: point, line and edge. For all this detection, for all these discontinuities, you having different kernels. You have to learn all these kernels. Okay.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.